let's see. I believe we're live. Yeah, we are. Okay, cool. Let's pull up this thing. And we'll isolate this. Hold on, I'm just posting the thing on the. One sec, I'm just posting the live link right here. Okay, I think we're good. All right, so yesterday, this was what we learned. I mean, I did it kind of in the review, but let's see how long the live is going. I think everything's set up. Cool. Don't use. So, okay, I mean, right here, we'll make this a separate thing. Let's see, that's not what I'm looking for. I think this is the chat that I was in. Yeah, that's what it is. So let's go. Right here it says functional version of agents working out. Linear algebra vector notation. Let me just grab my glasses really fast. Nope, not what I'm looking for. Oh, they're right here. So, sorry, I'm a little bit distracted. I like glasses. Let's respond to this. That's my first comment I basically got on all my live streams. Okay, 3 velocity fields. So basically what happened was we got all the way here, and I mean in the video I kind of explained everything. I'm just speaking out loud. I know like there's not going to be anybody actually maybe tapping in here, but I was talking about like the Feynman technique, which is like he said explain it to yourself as you're going along. So I mean, like I said, prove a process, and maybe I'll just be able to talk just in case. I just want to be able to understand this audibly, so to look back at. Roll the velocity distributions, calculate the strain rate. Okay, let's brush up on this really fast, because what are our definitions? I wonder if it can do one of these right here. So okay, cool. Yeah, it was so, I'll tell you how, I was so novice I had to literally ask, like, what is a duct? Like, I knew what a duct was, I just, I was, like, so taken aback by the gibberish and not the gibberish, but the terminology in the problem set that I was like, everything could mean something else here. So, a duct is a duct, though. I know that now. I'm showing how fast and in what direction the fluid moves at every point. Got that. We learned this. Good velocity, laminar flow, vorticity. Okay, let's go. Google. Yeah, so apparently I've last night I basically looked at or I went deeper after I hopped off the live stream, and this number this term keeps popping up everywhere, Reynolds number. So I think that's gonna probably be of some importance. Maybe I'll just like make a side reference here saying like to look more into that. Maybe we could use this as kind of like a journal. So what is the date? 10, 14, 2000. I'm not looking there. Cool. Yeah, so I need to understand what that relation was to the. Let me just make sure I really have this done. I also have my notes. Give me one more second. I'm gonna grab my iPad. Yeah. Okay, can't find it. We'll do the Google Docs style. We'll just notate over here. Cool. Maybe we should do it all on one screen, but yeah, that's okay. Okay, I understand that, the Reynolds number. So I guess I did want to brush up on vorticity. And also just kind of find out what does... Love it. Oh, who's in here? So, okay. So it already has the document loaded up, so we can just straight up hit it with one of these. So for the record, I was talking about this in my live stream yesterday. So I mean, as far as reviewing goes, I basically found understanding of some of these things in different areas of the prompts. So if I were to just ask it to summarize everything right now, and we'll do that in a sec, but it won't necessarily like, it won't really pick up on the very specific parts that I'm interested in or that I found understanding in when I ask it for the summary again, unless I'm explicitly like, okay, I understood that part of it, and I'm just good at prompting the GPT. So, I mean, I mentioned this kind of in the video, like it's. I mean, look, this is my context window right here. And if I literally like asked it, I don't even want to because I know it's going to show me a really like disorganized. I kind of use it like a scratch book. My head is going to go in all different places. If I asked it to summarize my prompts, it would just be like, what is this? What is, or it would just show like the list of questions I asked it, which it wasn't a very strategic line of questions. It was just kind of like, what is this? What is this? Maybe like, what does this have to do with rocket science, for example? So it's, unless you're disciplined about that, like you are running into, and I doubt I am like completely terrible at it, but I'm like, look here, like this is our entire context window. So yeah, like obviously, no taking on the side, finding our stuff here, but yeah. So let's mess with step F now. So we have right here. Where is our part F? Download the file. Yes, please. Consider a slice of the fluid between. So let's ask it to break it down. So I'm obviously very lost about that. Let's first ask, like, what is this? This is half of the battle right here, just like making sure that you have understanding over these individual, like all the moving parts here, or all the definitions. Dynamic viscosity. Let's go step by step. Okay, good. Dynamic, pronounced mu. Okay, good to know. Measures how. Okay, understood. It's basically the fluid's internal friction, so an air. Okay, I understand. Higher U means flowing easily, so understood. Okay, in math form, that's good for me because I think we should practice this. Makes sense if he was small. Yeah, I really appreciate the intuitive examples because like sometimes this gets lost in my head, but it matters most in rocket science. Good, I like that. Um, why it matters in rocket science? Okay, we'll we'll pull back here because that just looked super gibberishy to me. I don't even know what that was. Find the viscous force per unit length on a slice of, say y is equal to find in civil wars. How much force? Causes that force. Okay, we got this. You're trying to find a viscous force per length on a slice of fluid between two heights. H equals. Students, how much force is the rest of the fluid pushing on this slice? Force. The rest of the fluid pushing on this slice because of this. Okay. And sometimes it's healthy to just do one of these. Please explain part F to me like I'm a complete novice. I mean, because I am. So it's ChatGPT is gonna say something really nice off the rip. Like it's never gonna be like you're dumb. Perfect. Some real world beginner point of view. I love it. This is stickiness. How much does one layer of fluid pull or push on? Okay, understood. Okay, you got your duct again, two flat walls, fluid in between, forward flowing. Okay, got it. No picture of slicing the fluid. Looks like this. Okay. Okay, understood the slice of fluid. I didn't even realize, see, I thought it was like, but that would make sense. H over 2 and H over 4. Below the slice. So they tug on it. Tug. Oh, okay, understood. Understood. Velocity changes with height. Velocity changes. Why, yeah. There's friction between the layers called shear stress. Okay, we remember calculating this yesterday, I think. No, I'm lying, because dynamic viscosity, I think they explicitly said here that, let me just make sure I got my moving elements. So U du over dy is the mathematical formula apparently. So where does, so we gotta throw this, I get it, okay. So we just gotta multiply all of that, y over 4, h. So yeah, maybe just take the derivative. I'm wondering if you take the derivative before, or if you plug these values into y before or after you would do the partial derivative. Just to clarify, it said du over dy, I think. Yeah, du over dy, so. Yeah, I need this. Okay, because the speed's same everywhere, no friction between layers equals no viscous force. Cool, this is a linear. Shear stress is the same everywhere. Your top and bottom pulls cancel. Cause I'm thinking about the curves because it said yesterday that in the three examples that we had here, so these three, what do you call it? Where is it? Coué flow and whatnot. This flow. So I mean the curves are, one of them is just like flat out zero, another one is just like linear, but I'm trying to think what the curves, the last one is parabolic, but I think that's a measure of it's a measure of friction or speed. It's a measure of, yeah, like velocity, or du over dy is what I am thinking of here. So let me just clarify that. What is the shape of the Poiseuille? I don't even, is it like this? Man, I don't remember. Poiseuille flow. It's Poiseuille apparently. I remember that, Poiseuille. What is the shape of the Poiseuille velocity? So this is a velocity equation, is parabolic, yeah. Okay, and they told me that, so I don't even know why I did that really roundabout way. This is your three velocity fields, it literally said it. Okay, that's great. Sometimes you gotta put those two together, so. So okay, let's go back. So shear stress back here. So speed increases evenly with height. Shear stress is the same everywhere. Top and bottom pulls cancels. So I'm gonna document this down. I'll just combine the notes I had from yesterday with this, but. Shear stress. Let me remind myself here. Where's the document? Strain rates. I'm pretty sure strain rates is like what they're talking about. So I'm also gonna put that in the document right here. Brush up on strain rates. Matter of fact, we're just gonna do this today, right now. Not what I'm looking for. Top card moves fast, the bottom card moves still. Oh, okay. I actually like that this is talking about drag because in rockets, every time I like search up one of these topics and I'm just like, what does it have to do with rocket science? It always has like, it's, I mean, like the result that always comes up is just something like, what does, or it will be like how best to optimize drag. So like that's just like the name of the game. It's just like how do we escape all of the whatever when we're launching. So I mean, part of the Feynman technique is just like applying or asking why this actually matters. So, I mean, I can't help but one of my friends here told me today, like, bro, you want to make sure that you're not getting too caught up in the theory because there's like a really important like you just need you want to get right to the application. So I mean, and I also understand I'm just building the fundamentals here. Like I wish I could just get there right now, but obviously we have this. Okay, got it. I mean, I think I can just like summarize this into the math formula and just calculate how that applies. So I would like to see. Okay, I'm in here. This is for what? The bottom slice. Shear stress on top minus shear stress on bottom. Oh. So I guess okay. So it's a very like niche question. Like how do you? Okay, so you just. My worry here is I'm just learning how to solve this problem. So I might have to ask it for some follow-up examples here. Difference in shear stress on top. Got it. Keep on looking back at that. So my head's like completely in a different realm right now. Okay. Net, I get that you're just calculating the differences in two different heights, and in the uniform flow, because speed is the same everywhere, because it's just zeroed out, like everything is moving the same. The derivatives just cancel out, so 0 is equal, 0 minus 0 is just 0. Quay flow, it's linear, so increases evenly with height. And because we're calculating the rate, shear stress on top. And just remind me here, how is strain slash shear? Strain rate, okay, so it's just the derivative of fluid velocity on a height. Okay, so you're taking the derivative of a linear curve, it's just a constant, so it's the same everywhere. Same minus same is also equal to 0. That is what that is saying. Net viscous force equals 0. Cool. And then here, there is a net viscous curve. Is that what they want us to answer though, or do they actually want us to calculate it? So, I mean, I get it in a high level, but y by 4. So I'll ask it to do it for the they just set up. Oh, here it is. Boy. Let's go. While I was doing that, it was just. And we got some viewers, it's kind of cool. Hey, that's lit. Cool, let's go back here. Did it give me my answer? Yes, it did. Okay, so given this and shear stress, y by h, y is, let me just look at those original formulas. Y by h, y is equal to h over 4. So, I mean, okay, let me just do this by hand. I got... W over 2 times 1 plus, what was the first value? It was top minus bottom, right? Shear stress at top minus shear stress at the bottom, I believe so. Okay, y is h by 4 over 4. And that would just be over h plus 1 this times uw over plus 16 16 16UW over HZ. By H. Okay, we're almost here. Come on, I got this. Okay, here's the formula. And then what is the outer term? It's UW over 2. That's exactly what I calculated. Okay, so I got UW over 2 times, or plus 16UW over Z. And then you just got to derive that. Fortunately, I'm not deriving it, but I'll just throw it in the calculator. Let me just make sure that my math matches up here. 2xy y is equal to h over 2. Remind me what that is. I'm pretty sure that's u by, yeah, du by dy. Okay. It's not that. I think it's that in this example because they explicitly say that this is u. So it's just whatever that is times du by dy. Du by dy, yes. For the velocity distributions. Got it. Cool. So let's pull up the old trusty derivative calculator. This never hurt anybody. Du by dx, fine. Oh no, there's two variables though, right? Can we change these? Never did multivariable. I always was blessed, or like my classes never had me, or derivative calculators really made a lot of sense when it was just like a single variable. But the other variable we're dealing with here is uw, and then we have one variable h, du by dy. I think what I said made sense, so let's see if we can answer this question right here. We'll just be like whatever the derivative is of uw by 2 times. I mean, that's such cheese. Like, this is working smarter in a way. It's just like not working so smart that you're just like vibe coding the entire thing. Just be like, give me the answer. UW, we'll put this in a parenthesis just so it knows what's up. And just for practice, I'm sure that it actually just knows what's up, but by 2 times, what was it? It was 1 minus, here, it's right here actually. 1 plus y by h, 1 plus y by h, so 1 plus y, which is h by 4 divided by h, bang. 1 plus all of that stuff, whatever the derivative is of uw by 2 times it literally just said it. So I just said nothing. Oh, yeah, that's what okay. I forgot I was asking about that flow, but. Oh. Exit page. Okay, so it's just gonna tell me how to differentiate it, but I think it's just simplify. Oh, I didn't realize that this is a constant. U at 0. Is that what it says? Oh, it does. I completely missed this. So, yeah, okay. So this can get thrown out of the differentiation. I get this. What's the formula? 1 by y h. So right here. Okay, fine. So I get it. You can just derive that and then. The difference in this minus the difference in that. Okay, that's what it says. The formula that they're plugging in is the derivation of plugging in. So okay, bottom slice. Let's do top slice. Whatever, I get it. You plugged it in. You got this value minus, or is it actually plus 2h? So why is that 2h? Oh, because of, okay. You add them up and you get, all right, let me just see if I can do this myself. Like, I just want to make sure that I'm not just swallowing the information like straight up. Like it feels, I don't want to just be like, head nod, I agree with everything the GPT says, because that's not the goal here. It's meant to help you. This is meant to help you think actually. So I just want to see how they derived it first, okay? Differentiate after they differentiate. Okay, so the differentiation is, yeah, we'll ask how they differentiated this. Nope, none of this. Right? Is that what I searched up? Did I do that right? No. Oh, wait. I totally know how to do I? Y by h is h over 4. Wait. I got this. I don't know why 1 cancels out. You're just left with, stop, dude. You're just left with y by h over 2. H can be replaced. I wonder if y can, let me ask it if I was able to, could I replace h by 4 into y before I differentiate? Was that a thing I could do? Come on now. I don't know if GPTs are just tweaking. Okay, fine. I think it's also just lagging up a little bit. Let's see. Let's just see. Maybe it's on Twitter. Nope. It's just a me thing. That's okay. My man Suhas. I reached out to an old friend. We were very close at one point. Okay, so it's up, but. So remember the rule, differentiate first, substitute later. Got it. Okay, fine. Y by h over. So I mean, I was asking because it would have just been easier to deal with one variable. So let's just see how they differentiate first. Okay, it's equal to 2y. Here we have it. Differentiate. Okay, got it. I mean, you know what I'm talking about, friend. No, I don't want both, buddy. The a squared by y squared, fine. Is this the... Okay, remember my derivation rules. Y is, yeah, y goes to the bottom, fine. Good. I know, my bad. Okay, cool. I'm gonna actually start doing my derivations by hand, just so I don't skim over this. So okay, case in point. Let me see if I can explain this correctly. So, first of all, dynamic viscosity. Force per unit length exerted on the slice. And so let's just clarify really here, just so I can explain this right. U times. What does, here, actually, somewhere up here. Insane. Sorry, that was an intense message I just got there. Just gotta pretend like that didn't just happen. Yeah, so back to the prompt. I wanted to find out what u by dy over dx is equal to, right? Differentiate the velocity, I know that, I know it. What is the dynamic velocity times du by dy? Is that, I want to know how that's calculated right here. Viscous force is equal to viscous force. Dynamic velocity times, or viscosity times the time speed changes as you go up in the height, and du by dy. Is that what we've been calculating the entire time? I believe it is. It's not du by dh. I don't think that's what we were calculating before. Let's just make sure. Somewhere in this massive context window, we're gonna add another one. New chat. Keep track of definitions. Oh my god. Okay. Dude, it's just too much, bro. Okay, so here's the explanation that I will work with in my head. So in the duct, 2 different points. Speed generally changes with height depending on whatever velocity fields we have. So in the example of a uniform flow where everything is just moving the same, at any given height, there won't be any friction. So in that case, there is no viscous force, which is calculated by, I mean, you can honestly just cancel out. You don't need to calculate. You don't need to do the whole entire derivative stuff. You should just know that the derivative of a constant is 0. So when you plug back in h by 4 and h by 2, I mean, it's unnecessary. You can just, there's a 0 term there. It's multiplied 0. Bang. Number 2 is when you derive it, you're left with a constant. So when you take regardless of what your heights are with this linear function, once you derive it, you get a constant, so it doesn't matter. You subtract the constants and they're equal to 0 once again. And then in the case of the Poiseuille, which is what I was like I was ripping my head over here, was like it's parabolic, so it converts to some linear derivative. So regardless of what, or it will be calculated by some factor, some variable factor, not like the other 2 forms. And that's what we're doing right here. So case 2. So is y by 4. So I mean, what happens when you throw in, where do they throw in the h by 4s and stuff? Okay, so it looks like when you actually do the math, when you actually differentiate the function, you get u at 0 over h minus, that's the top layer, that's when h is by 2, and then du by dy is equal to at h2 it's equal to u0 over 2h minus negative whatever we have right here. So when you subtract them, you're just left with, you can honestly just take out one of the ua by 2h's. I mean, they cancel out. So you're just left with one u0. You're left with negative. Are you still left with? Negative, is it, yeah, you're left with negative u0 over h, I believe. So, I mean, let's see, let's just double check. So what's the answer? Is the answer to part F for what is it called? My head's a little bit frazzled here. Is the answer to part F for Poiseuille? You know, this is where I'm at. Poiseuille. Negative u0 over h. Please? Oh no. No. Was it positive, man? What was? Oh god. Okay, what's wrong here? Ah, whoops. Oh, looks like I'm wrong. So you just add, you add up. Let me just do this correctly. Oh, I want to just break that down for me. That makes sense. I just want to make sure that I mathematically understand what's going on. Mathematically. I had to throw in the Italy right there. Minus. Oof. Oof. You know what's hilarious? When I literally just copied and pasted that, whatever it told me earlier, it literally was just like, that's not actually how you format it. I'm just like, I copy paste exactly what you asked. I just copied and pasted what you wanted. Okay, I get it. Fine. Understood. And give me the intuitive explanation. for the Poisson. Excuse me. Just change the height, top and bottom poles don't cancel. There is a net viscous. I get there is a net viscous force. And you know what? That's honestly good enough. I get there is just a net viscous force. So, okay, I mean, working example. One, in the case of a uniform flow, it zeroes out. There's a zero term already. With constants, you just subtract the same constant. It doesn't matter. It'll literally just be dynamic viscosity, whatever they gave us. What is that? Mu times whatever constant this pumps out, minus mu times whatever constant this pumps out. So zero all around, and we just calculated that. What was it? It was like negative mu, u subscript 0, u at 0.0 over 2h. So that's like the mathematical derivation, but it just means that there is, I mean, you can, this was like last class, but linear or parabolic goes down to linear, so there's just bound to be, in this case, at the two different points, there is a difference. So that's what that means. I wonder what, it's not what I want to do. Omega XYON. I wish I could do a hand cam. That would be kind of cool. I'm going like, we're going, I wonder who this is. Omega XYON. Yeah, maybe I could do that. That'd be fun. I'm literally just streaming off of, I just have like my MacBook and I'm just like scrolling here because it's just easy. I wonder if that person's still in here. Thanks for the comment, dude. You're actually just like the first comment that I don't even know who you are, but appreciate it. Thanks for the question. It's probably a good idea. Maybe I'll do that. You know who this is? Oh, my man Mike. That's so fire. That's love, bro. Okay. So, I mean, cool. I hope the intuitive explanation was good enough. Basically, I mean, I'll really try to break this down, and then we'll just jump into problem 2 over here. We'll try to really run it down. The problem basically, I mean, like you can see it here. The problem said there's a duct, water or fluid, because this is fluid dynamics. Water is flowing from left to right, and it's a 2D duct. There's no it's not popping in or out of the screen. So uniform flow means that everything, the speed is just all the same throughout. There's nothing changing. And these are example of, I mean, if you watch the video, it's laminar flow. So all the sheets, and you can imagine fluids as like sheets of parallel layers, and they're just flowing uniformly through this duct. And they're very predictable. In the case of uniform flows, they just go straight up. The speed of all those sheets are the exact same. With the Poisson, that's actually how you say that. At the top layer and the bottom layer, there's more friction. That's what basically that equation means. And as you go in the middle, it's smoother. So it does change with height. And so, I mean, at the top, it's really, really hard, and then it's fast in the middle, really slow. So it's, parabola. And then Coué flow is, it's a linear function, and so it just changes very directly as you change h. I don't know. It's something like that. I know that was probably a poor explanation, but that's hilarious. I agree, bro. I'm really trying to wrap my head around this. I think it's like slowly but surely we're getting there. Vortices. So okay, number 2 right here. We will look at the velocity behavior of vortices. So right back to definition land. Also, Mike, this right here has been helping me, bro. Like there's a study feature on ChatGPT where it won't just like give you the answer like straight up. Like I know I'm like it's so easy to just plug and chug and just be like, yep, that's what I want. That's what I want. Kind of like what I'm doing, honestly, but it kind of just like guides you there. It doesn't like just be like, this is the answer. So that's kind of cool. But let's ask it what we need. The most beautiful and important ideas in fluid mechanics, vortices. Let's go step by step and keep it intuitive first and connected to what you already know about vorticity. Great. So, what's our number, by the way? What are we doing? 114. Picture is water swirling down a drain. Okay, that makes sense. That I've heard of. This is one of those things where I ask what is a definition that I think is like some super complex thing that's like duct. Like I literally had to be like, what is a duct? Because I thought it was like some super physics term, but it's not. It's just a duct. Same thing here. It's a vortex. It's just like a swirl. A little swirl down a drain. Is the vortex the core where the rotation is the strongest? Water pressure lower in center. I get it. I know what that means. Pressure lower in center pulls fluid inwards, causing spin. I can just imagine that intuitively, so let's just pretend like I have shear between, bro, the terms are killing me. Shear, remind me what the shear is. It's a type of strain rate, right? It's a very certain type of strain rate. Yeah. Deck of cards, cool. It's a bit faster than the one below. Got it. It's the shear. Okay, fine. Shear is where it tilts. Okay. Yeah, got it. So what was it talking about with shear here? Yeah, y vortex. I will get there in a sec. Shear between the surrounding air rolls up into a donut-shaped vortex. Shear between in a smoke ring. Shear between the ring and surrounding air rolls up. The tilt between. Everyday example. So this is kind of like literally the only thing that makes sense. This is blowing my mind, but we're gonna mark that for the. Where is my Google Doc? I got one right here. Understand the air examples of vortices. Vortices. Vortexes. Vortices, yeah. Good. Science behind it is a reason with high vorticity, meaning the fluid there has, high vorticity means there is strong local rotation pressure. And physics is hard, bro. It's so hard. Imagine engineering stuff out of this. Is what I'm trying to do. I'm really, when I was saying define rocket science, like, this is barely even rocket science. This is fundamentals, man. Something very difficult to understand. I get it. Vortex is the math that measures how much a spin a fluid element has. So remember? No, I don't remember that ever. When did you ever tell me that? Acting like I'm actually like smart. Spin a fluid element. So okay, high vorticity region is equal to strong vortex. We'll ask what that means. See, I get so sad because like it gives me a really quality answer here, and then as soon as I get stuck up on a part of it, like and I gotta break the context. So vorticity is just defined as the curl of the velocity field. So does that represent curl? Paddle wheel. I don't know what a paddle wheel is. Oh, cool. Oh, it's one of those things. Okay. A little spinny. Gotcha. Okay, gotcha. So okay, we're gonna start keeping this one as the definitions tab and this one as the, because it's just a scratch book right now. Okay, great. Sorry, it was just, well, high vorticity region is vortex region. So yeah, let me get back to my definitions. Thank you. Vorticity, singular. So what I'm curious here is how vorticity, or this is still not the right prompt. Let's go back. Let me also see if I can look for some more intuition in the, we will assume that the velocity in these vortices, vorticity, and just make sure, remember vorticity. velocity in this vortices. A vortex is a region. Okay, see, it was just hidden right there. Vortex is a region with high vorticity. So it's not a vortex if it doesn't have high vorticity. I wonder what the threshold is. That's just like, this is a high vorticity. I'm sure there is one. But what is a high vorticity? What is a classification for a vortex as far as vorticity goes? How vortices behave. They can move. Vortices. I'm trying to imagine. I thought it was just the entire, like, what's swirling. I thought it was inside the core where the rotation is strongest. Okay. So is it like a physical object? It's a region where the flow spins around a central line. Got it, okay. Yeah, I got you, bro. Let's link this right here. My brother. How do I? Man, I'm super new to stream, and I don't even know how to. Can I put a chat? Hello. What's up, chat? What's up, Mike? Let's go to YouTube Studio. Nope. Content, live, go right here. I need the live link. YouTube Studio. Can I just, oh, I can't chat. Or sound. There we go. Easy, yes sir. So let's get rid of this. I should be able to type in OBS. I don't know why it's not letting me. We'll figure it out. So, by the way, this is in the course. Like, if you just search up this, like, where I'm trying to get a grill down on. Basically, my mentality was, so I'm gonna get out of this. I probably should take a break on my head. I was trying to do, the idea is like, why am I learning rocket science? Like there's actually gotta be a reason why I'm doing it. So we got it right here. We could do a simulation, or we could just make an extremely basic version of a projectile, or like, you know, it's rocket science, like make a rocket. And I'm also trying to figure out how to learn, obviously, like what's best. I'm like sending it to the max here by doing rocket science, something that's like, obviously you could see it's hurting my brain, but grilled down on foundations. So this is, aerodynamics is super important for that. So that's my mentality doing this problem set. And this is literally the first assignment, dude. Like there's 9 of these. I can't even imagine. All right, we're gonna go to the laminar. No. I don't know, bro. This is gonna be the end one. Let's just see how nasty it looks. Okay, it looks friendlier, to be honest, than what I'm doing right now. But we're gonna continue doing it. So these are 3 vortices. These are 3. So let's find out if those 3 represent 3 different. Okay, enough of all this. In problem 2. Does UR U0? Is that a theta? Okay. Does UR u theta and u, no, that's what I mean. Not your, bro, I feel like it looks so weird. And then what was the last one? U, Z represent vortices. They're just velocity components instead of cylindrical coordinates. So I don't even know what a cylindrical coordinate is instead of rectangular. So help me out here. What it means? Motion straight. Bro, Mike, what does that mean right there? This is about to send me. What is the azimuthal direction, bro? No, we have a definitions tab here. Okay, so it just means in a circular motion, but they had to just call it azimuthal. That's okay. I forgive. Exclusively used. Okay, fine. You know, like something TikTok, that's kind of cool. So back to the board. Velocity component is equal to 0 here. It's equal to itself times r, which I'm guessing is radius because these are cylindrical coordinates. And then also equal to 0 dot. 0 dot. You know what? We're just going to ask GPT for this type of velocity just to prove that the only component of vorticity which is possibly non-zero is the axial component W subscript Z. So I'm gonna hit it with one of these. Explain for question for problem 2, part 1, part A. So these are cylindrical coordinates. Oh, that's what it means. Okay. See, this makes more sense. Those are just coordinates the entire time. Hey, bro, somebody threw my video on their favorites. That's good. I like that. I'm really an influencer now, I feel like. Anyway, cylindrical coordinates, got it. Determine whether the flow is. Then it asks you to do something like, let's just make sure. Prove that the only component of vorticity, the only component. Okay, so. And this is equal to vorticity, so that's a divergence question. You're checking if, then what is W subscript Z? Is that W, by the way? Okay, it'll explain it to me, so it's gotta be right. What does W subscript Z, W subscript represent? So it's Z is the last coordinate for the cylindrical thing, but okay, vorticity at that point. Yeah. The divergence is zero. The flow doesn't expand or shrink, meaning the same amount of fluid enters and leaves any small volume. Okay, so I'm in limbo right now. We're gonna ask it. Okay, really break down this question like I'm a novice. Oh my bad, bro. I should probably have this chat like active. I don't know how to do that, but let's see. Let's just finish the definition. So it's cooked. Let's just read the full thing. Not that we're talking about. We're talking about this right here, right? Not subscript Z. Is that what we're talking about? Mr. Yeagle? That's okay. Okay, so calculating vorticity when it's equal to 0. I'm just wondering why it says that when the only time that it's equal to subscript is the axial component. So we'll let it tell me what's up, and then maybe that can give us some clarity. The divergence is 0. The flow doesn't expand or shrink. It asks you to do something like determine whether the flow is incompressible. Flow doesn't expand or shrink, meaning the same amount of fluid enters and leaves any small volume. Got it? Okay. Yes, please tell me this. This is exactly what incompressible. So wherever the fluid flows, it fills space without piling up. Oh, okay. So like. Okay, so I'm trying to think of a vortex. So incompressible means that it's just like no amount, it's just like a constant flow of water. Like there's no shifting up or shifting around or leaving gaps. Or even if there is, it's just constantly like, if it was, then maybe the vortex would not form, I guess, because, yeah, divergence formula is. So we got a divergence formula. Okay, this is the divergence formula. This is throwing me crazy. That's okay, though. It will tell you. If it equals 0, meaning divergence is 0, the flow doesn't expand or shrink, the same amount of fluid enters and leaves. Okay, if that is 0, the flow is incompressible. You can't squeeze or stretch it. Okay, we'll just directly loop that into here. So we'll just say divergence at 0 is incompressibility. If not, fluid is either accumulating or depleting somewhere. Got it? Does the given swirling flow conserve volume? No compression or expansion. Would you like me to? Does the given swirling flow conserve volume? No compression or expansion. Okay. And see, that is helpful because right here it's just like one of the axial component. Which Prove that the only component vorticity which is possibly non-zero is that one. Prove. Okay, so let's continue. Is Mike in here? It was the weird A word. It was the weird A word. Oh yeah, we got a definition, right? Azimuthal. Yeah, so swirls around the center. Yes, sir. It's azimuthal, yeah. Good connection. So let's see if we can continue with this. Okay. Got it. A divergence step by step I would, but let's just see if... What is a curly W? Curly W vorticity measures. Vorticity is a vector, understood. Cylindrical components though. Axis of spin. Fine. I also thought that vorticity. What is delta by U? Okay, so this is a different formula. Vorticity is a vector, meaning it has a direction and size. Cool. Has our three components in plane words. It's how fast fluid spins around the z-axis. Okay, which I understand. If you look straight along out of the page, yeah, I get it. If it's a rotate counterclockwise positive or counterclockwise negative in the xy direction. So it's just asking. Yeah, okay, I understand the intuition there. So it's asking me when to prove that the only thing actually maybe affecting the super pristine hypothetical vortex is this kind of spin right here. Like if that's gonna make it expand or shrink, if any. So let's see. If it is asking you for something that is not equal to 0, then is it asking for something that is also no incompressible? Yes, I believe so. So intuitively that means is the vortex not like uniform? Is it like I mean, whenever I'm like in my head, I'm picturing like just a swirl of water. So if no incompressible to me means like compressible means it's like doing one of these. Incompressible, whatever means like equal to 0, divergent as they call it in your duct tape flows. So let's go. In cylindrical coordinates, not the flat XY grid, got it. Or how far you are from the center radius, got it. The angle around the axis, okay, kind of got it. Height or distance. Fluid has 3 parts, got it. Velocity of the fluid has 3 parts. Yeah, they've specified right here. Okay, 2 of the components are 0. One of them is just dependent on your R. Your R, and they'll probably, is the flow incompressible? Got you. So, okay, so this is just like a plug and chug formula, it looked like. it's a vector. This is like some vector multiplication. The formula looks like this. Each term checks one direction the first. I want to really grill down on the math here. First term checks one direction. Got it. Okay, so this is like a 3 vector. So like whatever. These represent something like this. Yeah. Okay, got it. Makes sense. Multiplied by upside down delta, and it clarified up here what that was, which is what is it? W vorticity. Vorticity is equal to which axis the fluid spins around and how strong that spin is. So U represents how strong the spin is. Upside down, I don't know what Greek. No, that's not what it is. How strong that spin is. Okay, cool. Do the given. So I guess if it's non-zero, if we have this formula, I wonder where. Yeah, so it won't do that. We have to take it out of study mode. Study mode, yep, I get it. We can do it in 2 tiny steps. Let's do it. First, I need the actual velocity components from your sheet. So let's go. U of R is equal to 0. U of theta equal to U theta times R. U Z equal to 0. See if that understood my notation. Great, now plug those into the cylindrical divergence. Wait, okay, let me do this by hand. Mike, I'll show you my math in a second here. How long have we been streaming for, bro? Time has been flying. Or not flying, it feels like hours. I wonder what does it mean by this? I think I can just ask ChatGPT that. What? Fine, only depends on how far you are from the center. Oh, okay. Got it. What throws me off is it just saying that U theta is just a function of R? That's what my brain's doing. U theta is just a function of R. Because I'm like, I don't think you can do like a divide by r and then u theta automatically becomes u theta divided by r. No, I don't think you can do that. I think it's saying that it's just a function of r. No theta or z dependence. Got it? Quick check. What is this theta component? If u theta So I'm gonna do myself a favor. I'm gonna take it out of study mode. So the prompt is left completely. Would that not be just 0? I'm gonna be honest with you. I think I'm not sure. So yeah, yes, I think it's all incompressible. I'm just wondering what they're saying when they say prove that the only component, which is non-zero, is the component this right here, the z coordinate for hold up, I'll let it stop here. Come on, come on. That's great, it completely derped. So yeah, we're all right. It's equal to 0. I get that reason its divergence is 0. So okay, let me just copy and paste it. What the fuck am I doing? Whoops. I didn't mean to curse. I was trying to keep it super PG the entire time. Would it not be the u sub theta? Yeah, that's what I literally thought. Like, cause, why did you stop thinking? So yeah, I believe. So I mean, maybe you're right. The problem I'm getting like thrown off is because okay, this. Let me just make sure I understand what you're saying. Use of theta, the weird 0. It's only part of the coordinate that is not equal to 0. Yeah, this, I think you're talking about this one right here, the u theta. But automatically it says prove that the only component of vorticity, which is possibly non-zero, is the axial component w at the z coordinate. So like whatever value that shit plugs out for this one. So I'm like, I thought, hello. I think I've asked it too much questions. It's absolutely like, bro, this is my context window. It's so like, look, I think it just deleted it all because there's just so much stuff I've asked it. Here we go. For velocity, the vorticity is this. Got it. WR. WZ. Got it. Substitute the given field. So where are we substituting 0 into? Everywhere here. This is equal to... Oh, because it's the derivative too. So I'm tripping. So derivative of nothing is just 0. Get it. Derivative of nothing... Derivative of r is also just 0. Given u r, uc is equal to 0. This component I get is equal to the derivative of some function of r. Okay, got that. And WZ, what do they plug in? I wonder. Oh. Okay, right here. I didn't realize that it was dependent on the theta value. So yeah, the only non-zero. Okay, I think I understand. Maybe that's what you were saying. Can I press launch? Can I press launch? I think the only thing that I was confusing was that the z component is dependent. Okay, so this I am totally just fucking overcomplicating this. So here, I'll see if I can just explain this for myself. I'm not even like trying to just be like, this is what's up. Vorticity. So first of all, vortex is an area where there is high vorticity. It didn't tell me what the threshold was. First things first. So we'll just draw down here. We'll assume that the velocity in these vortices is 0, and the circumferential direction only depends on these radial locations. Okay, so this is the vector. I mean, I'll write this down here. Vector 0, comma, some function of r and some function of z. So like that. Let me see if I can. I don't even know. This is not helping. What am I looking at? Okay, hopefully y'all can see that. Whatever, it's a vector. And then the formula for vorticity was that weird delta, W, or sorry, the weird delta U, and it's the partial derivative of those functions. It's some like linear, it's a vector where that upside down D and U and whatever their components are, we'll just, I mean, it gave me the mathematical derivation of it. So we'll just say that these are some row memorization kind of formulas for calculating W. Like this is just this broken down basically in cylindrical coordinates. And the Z component was dependent on the only non-zero part of this vector. So obviously it's not going to be 0. So Jesus Christ, that is what that means. And you know what? I'm not going to lie, that was like a very janky explanation of that, but we will look more into that. I think, or whatever, understand the meaning of, matter of fact, let's just ask it. What is the upside down delta symbol mean intuitively? I had said it above, I'm just asking it again though. Nabla. It's worth understanding. It's an operator that tells you how something changes in space. Cool, so that's obviously what it was doing. Nabla by your vector. Cool. So I mean, I think I understand the intuitive meaning. We'll just write this down for later. of W equals nabla. I don't even know where to find that. Nabla times U. Okay, I think that's fair. How it's used. Cool. And let me just look at the problem. I think we're gonna call it quits right now, but okay, yeah. All right, y'all. We're just gonna call that a day. I think we slowly but surely got there. One extremely difficult problem set, but yeah, we got there. It's also just gonna help. Like right here, it gives the recommended readings, and I can't find this because they don't link it, but it's something. So, all right, boys, I'm gonna head out. Cool. I wonder if I can just end stream right here. We'll send it from here. Right here, end stream. Cool.